Welcome back. In today's video, we're going to be talking about linear inequalities. We'll start off with a couple linear inequalities that students often have trouble with. We'll start off with y is greater than or equal to 10x plus 2. So we'll draw that one out. So 10x, so that has a slope of 10 and a y-intercept of 2. So slope of 10 is a pretty steep slope. And that's the reason why this one can be a little bit confusing. Because with a steep slope like that, where the line looks almost vertical, the common mistake is to think that this should be shaded to the right, because it looks like values that are greater than would be in that direction. But that's actually not correct. And the reason why is because notice our inequality has y on the left-hand side. So this says y is greater than or equal to 10x plus 2, where 10x plus 2 is the equation of this line. So when we look at an inequality that is set to y, we don't want to think of shading left or right. We want to think of shading up or down, because y values go up and down. So y values that are greater are above, and y values that are less are below. So in this example, y is greater than, so if the y values are greater than the line, that means we would shade up from the line. So it's going to kind of look like we're shading to the left, but again, we are actually shading above the line. So now there are instances where you do want to think of shading to the left and right, and that's when our inequality has x on the left-hand side. So something like x is greater than 2, for example. So if we were to draw that out, greater than 2, so that's a strict inequality. That would have a dashed line at 2. And greater than, so x values go left and right. Smaller x values are to the left. Greater x values are to the right. So if we want x values that are greater than 2, that means we're going to be shading to the left. So when we have our inequality set to x, we shade left or right. When it's set to y, we shade up or down. All right, let's look at a couple more. Another one that you may not have seen before or may not have graphed before is something like -3 is less than or equal to x, which is less than 1. So this is telling us two things at the same time. X is both greater than or equal to -3, and x is also less than 1. So we start reading here from the middle. So x greater than -3, x less than 1. So when we draw that out, we have -3 there, and it's less than or equal to, so we would draw a solid line through that. And then we have x is less than 1, and that's a strict inequality, so we draw a dashed line through there. And then, since x is greater than or equal to -3 and less than 1, we would shade in between those two lines. So it's just going to be shaded in between the vertical line at x equals -3 and the vertical line where x equals 1. All right, let's look at one more inequality. 2x minus 4y is less than or equal to 15. So we'll draw out what that graph would look like, or something close to it. Look about like that. So what we want to think about is whether we're going to shade above that line or below that line. So take a minute and think about it. Pause the video and think about where would we shade the line, above or below? So at first glance, it might seem like the answer is below because our sign is less than or equal to. But let's go ahead and solve for y. So we'll do that by subtracting 2x from both sides. So that'd be -4y less than or equal to -2x plus 15. And then we'll divide both sides by -4. That's going to give us y is greater than or equal to, because when we divide or multiply by a negative number, we have to flip our inequality sign. So that gives us y is greater than or equal to positive 1/2 x minus 15/4. And so what we can see now is that our inequality is actually greater than or equal to, which tells us that we're going to be shading above that line rather than below. So when you have the form, a form like this, 2x minus 4y is less than or equal to 15, which is called standard form, before you decide how you're going to shade a line, it's best to get it into slope-intercept form, y equals mx plus b form, so that you can read directly what the sign is. So greater than or equal to is going to be shaded up, less than or equal to is going to be shaded down, if you have it in this form. All right, so that's a little bit on inequalities. Next, let's look at a linear programming problem. So a linear programming problem is a problem where we are trying to maximize or minimize a function subject to some constraints. So what we have here is we want to maximize z equals 10x plus 10y, subject to the following constraints. 5x plus 6y is greater than or equal to 95. 15x minus 9y is greater than or equal to 150. X plus y is less than or equal to 42, and x and y are greater than or equal to 0. All right, so let's look at each piece of this. So first we have the maximize z function. We call this our objective function. So it is our objective. We are trying to minimize or maximize something. And that's how you can tell these problems apart from any linear system of equation problems. And if we're trying to minimize or maximize something, we have to be dealing with inequalities. All right, the subject to part, these things are what we call constraints. So they are constraints because they have inequalities. The last two of those, or really it looks like one, but it's x is greater than or equal to 0 and y is greater than or equal to 0. That one, we call these the non-negative constraints. So non-negative constraints, because they constrain x and y to be positive values. And the reason why they do that is because once we get into word problems, x and y are generally a number of items of something. And so you can't produce or sell a negative number of items. So they need to be positive. All right, so those are the three parts of our linear programming problem: our objective function, our constraints, and our non-negative constraints. The non-negative constraints will be a part of every single word problem, but not necessarily every single problem. But if it's a word problem, you need the non-negative constraints. So make sure not to forget those. All right, so next up, we want to take our inequalities, which are all in standard form, and put them into slope-intercept form. That way we can graph them in the graphing calculator. All right, so the way we'll do that, let's take this first one. 5x plus 6y is greater than or equal to 95. Let's subtract 5x from both sides. So that'll give us 6y greater than or equal to negative 5x plus 95. We'll then divide everything by 6, so that's going to give us y is greater than or equal to negative 5/6 x plus 95/6. So we are going to number each of these, and I'll also use colors. That way when we're graphing them, we can see them a little bit better. So we'll use blue for this one. So we have y1 greater than or equal to negative 5/6 x plus 95/6. All right, let's do the second one. 15x minus 9y greater than or equal to 150. So we'll subtract 15x from both sides. So we get negative 9y greater than or equal to negative 15x plus 150. We'll then divide everything by negative 9. That's going to flip our sign, so y is less than or equal to, this can be positive 15 ninths x plus 150 ninths. Now we can reduce those if we want to 15 ninths and, oh sorry, that's a negative 150 ninths because we divided 150 by negative 9. So sorry about that. Y is less than or equal to 15 ninths x minus 150 ninths. So we can reduce those. 15 ninths x could be reduced to 5/3 x, and then negative 150 ninths could be reduced to 50/3. But we don't have to because we're going to plug it into the calculator, so we don't necessarily need to reduce. All right, so we're going to call that one y2, and we'll make it green. All right, our next inequality, x plus y less than or equal to 42. All we need to do is subtract x from both sides, and we get y less than or equal to negative x plus 42. And we'll call that one y3. And that one will be red. All right, so our last two, x and y, are both greater than or equal to 0. Y is greater than or equal to 0. We can put into our calculator. So y greater than or equal to 0, we'll make that one y4. But x greater than or equal to 0 cannot go into a graphing calculator. We can only put in y's. All right, so let's put these into our graphing calculator. We'll press y equals. All right, y1 is negative 5/6 x plus 95/6. y2 is 15 ninths x minus 150 ninths. And y3 is negative x plus 42. And then y4 is 0. All right, so we have all of our inequalities in our calculator. So now we'll hit graph. All right, so now it's graphed, but we really can't see a whole lot. So it'd probably be helpful if we zoomed out. So we're going to hit zoom, and we'll go down to zoom out. We'll press enter, and then we also have to press enter again to zoom out. All right, so that looks to be good enough to where we can see our function well enough. So what we're going to do, we can use the trace button, and that tells us which line is which. So the line we're on right now is y1. That's the blue one on our screen. If I press the down arrow, I can see that's y2. So that one is the positive slope line. And then down again, y3. I can use the left and right arrows to move that cursor. I can see that is the negative sloped line that's on top. And then up or down again, we can see the pink line there, that's y4. Now, there are ways to have your calculator shade for you. With this many inequalities, sometimes it ends up just shading everything, and it's kind of confusing to see. So what we're going to do is we are going to shade it ourselves, and then we will go from there. So let's go ahead and draw it out. All right, so if we go back to our calculator, we had y1 had a negative slope. It was blue. It kind of went like this. y2, that was the positive slope line, and it crosses y1 above the x-axis, so something like that. Now, we don't have to draw this perfectly, but we do want to make sure that at least our lines cross in the right places. So y1 and y2 intersect above the x-axis. That's important for that to happen here as well. All right, and then y3 was also a negative slope line, and it also crosses y2 above the x-axis. All right, so let's label these. That was y3, this one's y2, and then y1. All right, so now let's go back to our inequalities. Y1 was greater than or equal to, so that one we're going to shade above the line. So I'm just going to shade a little bit above the line just so we can kind of see where it's going. Y2 is less than or equal to, so we're going to shade below that line. And then y3, it was less than or equal to as well, so we'll shade below that one. Then we're also told that x and y are greater than or equal to 0. And so that means we are constrained to the top right quadrant of our graph, which is what we see here. So x and y greater than or equal to 0. X greater than or equal to 0 means we have to be to the right of the y-axis. Y greater than or equal to 0 means it has to be above the x-axis. We have to stay in quadrant 1 of our graph. All right, now that we have everything shaded, we want to find our feasible region. So the feasible region is the region where everything is shaded. So we want it to be above y1, below y2, below y3, and then also x and y both need to be greater than or equal to 0. And in this case, that is this area right here. So that is our feasible region that I have highlighted in yellow there. It is below y2, it is below y3, it is above y1, and all x and y values are positive in that region. So that feasible region, we can pick any point in that feasible region, say that point right there, and we could plug it into all of our inequalities that we started with, all of our constraints, and all of them would be true statements. So we plug x and y into the first one, it would be greater than or equal to 95. We would plug it into the second one, it would be greater than or equal to 150. Plug it into the third one, it would be less than or equal to 42, and x and y would both be positive numbers. So that's what our feasible region is. Now, there won't necessarily always be a feasible region. It's possible for there to not be a feasible region, so make sure to look out for that. All right, now that we have our feasible region, we have a theorem called the corner point theorem that says if there is a maximum or a minimum of a feasible region, then those will occur at corner points. And so the corner points are the intersections of the lines that we're dealing with here. So the intersection of y1 and y2 is a corner point of the feasible region. Intersection of y3 and y2 is a corner point of our feasible region. Also, where y1 intersects the x-axis and where y3 intersects the x-axis. Those are all corner points of our feasible region as well. Where y1 meets the y-axis and where y3 meets the y-axis, those are not corner points of our feasible region. They're intersections of the lines that we shaded, but they are not corner points of our feasible region, so we don't need to know those. Though if we did, we do already know what those 2 points are. They're just the y-intercept of those two lines. All right, so next step is we want to find the intersections of these points, so that way we can plug them into our objective function. So there's a couple different ways of doing this. We'll start off by finding where y1 and y2 intersect. So those lines are 5x plus 6y equals 95, and 15x minus 9y equals 150. So those are the lines, not the inequalities, but that's y1 and y2. And so if we want to find the x and y value those two have in common, well, this is something that you're probably familiar with. It's something we've done a number of times in this course before, and that is we're trying to solve a system of equations. So we will take our calculator. Let's go to Matrix, over to Edit, put in a 2 by 3 matrix with the coefficients, so 5, 6, and then our constant 95. And then coefficients 15, -9, and then constant 150. All right, we'll quit out of there. Second matrix, over to Math, up to RREF. Select matrix A, and then press Enter. So we get the x is 13 and y is 5. So 13, 5 is that point. So that's one way to do it. Another way is we could use the intersect function on our calculator. So let's do that for y2 and y3. So to do that, we'll hit Graph. We'll press second and then the trace button for calc, down to intersect, press enter, and then we want to select y3 and y2. So it's on y1 right now, so we'll press down 1. All right, we're on y2, so we can press enter. Moves us to y3, which is the other one we want, so we can press enter again. And then it says guess down here. The only time we'll need to guess is if we had nonlinear functions, that is curves, lines with curves, which we're only dealing with linear functions, so we never have to worry about that. So we can just press enter again. All right, and it tells us that that intersection point is 2220. All right, so next we want to find where y1 and y3 intersect the x-axis. Well, there are a couple of different ways to do this as well. So we can use the intersect function because we put y4 as the x-axis. So let's do that for y1. So let's find the intersection. So second trace down to intersect. So we want to do y1, so we'll press enter, and then y4. So we'll press down until we can see y4 up there in the top left. Press enter, and then enter one more time, and we see that that is 19,0. But we already knew one of those values because it's on the x-axis. So we know the y value is 0. So this next point over here, we know the y value is 0. And we know that equation is x plus y equals 42. That was our y3 equation. And so we could also solve it by just plugging 0 in for y. X plus 0 equals 42, or x equals 42. So we know that our x value would be 42. So the intersect function on your calculator is helpful. It won't always work, however. Sometimes it will give you decimals that you can't change into fractions, and for the homework you'll need fractions. Or sometimes, like if you tried to do this one, it would have given us an error message. And the reason why is because we are not zoomed out far enough. If we had zoomed out one more time, then it would have been able to find this. The calculator is kind of quirky like that. But anyway, so lots of different methods to find the intersections of these lines. All right, now that we have the intersections of the lines, we want to find our maximum. In this case, this is what we call a bounded region. Bounded region is a contained region, so I could draw a circle around it. A bounded region will always have both a minimum and a maximum. An unbounded region would only have one or the other. And in this class, we really only look at unbounded functions that are shaded in the up direction. So our unbounded functions don't have maximums. So, but a bounded region like this one will always have both a maximum and a minimum. So we wanted to maximize z equals 10x plus 10y. So all we have to do now is plug each of these in to that function. So 13 and 5, for example, we plug 13 in for x and 5 in for y. So that's 10 times 13 plus 10 times 5. So that's going to give us 130 plus 50, and that's going to give us 180. We'll do the same thing for 19 and 0. So 10 times 19 plus 10 times 0, that's going to be 190. 2220, that's 10 times 22, and 10 times 20, that's 420. And then 42, that's 10 times 42 plus 10 times 0, that is 420 as well. So in this case, our maximum is 420. But it occurs at two different points, and that's okay. We can have the same maximum value occur at 2 points. And actually, what this also means is that every single point on the line segment in between those two intersection points is also 420. But so if we were asked where our maximum occurred, what corner points our maximum occurred, we would say at 2220 and at 42.0. But we have just one maximum value, and that is 420. All right, so that's linear inequalities and linear programming. I'll see you next time.